Today's lecture is all about system similarity. We're going to talk about how 4 of the domains in this class, in particular, we have mechanical translational, we have mechanical rotational, we just finished our unit of electrical, and we have one more domain that we're going to explore in detail, and that is fluidic systems, or fluid. And we're going to develop a little chart right here, so I'm going to make a couple of different columns, and I'm going to label this first one as effort, and we'll talk about here in a second. Flow, momentum, and this one is displacement. And we're going to break these up into 2 categories. The first, or rather the ones on the right, are called energy variables, and the ones on the left are called power variables. So when we think of, let's say, the power in a gear, okay, we've got maybe a small gear here and a big gear here. We know that the power in is going to equal the power out. And if you recall from those previous lectures, we had that this power is going to equal the torque times the angular velocity, and that might be on the, let's call that 1, let's call 2. On the first side is going to equal the torque on the output side times the angular velocity on the output side. We also have power in a electrical circuit sense, where we have some sort of voltage right here, and we have a current through this resistor, and the power in the resistor is going to satisfy the equation voltage times the current. Well, we've got then 2 variables, okay, voltage and torque, which are kind of external to the situation, that they are driving something and causing something else to rotate or to flow or to move, angular velocity, or right here, the current. What this means then is that in this chart up here on the left, we can fill up this column with a bunch of power variables and express the power by figuring out what the effort variable is. In this particular case, we know that we have torque right here, and we multiply torque and effort variable times the flow variable. In this case, it's the angular velocity. We get power. We've seen that the effort variable is voltage, some sort of external pressure on the wires, a separation of charge such that the electrons are going to flow through that resistor, and we multiply that effort variable times a flow variable, I, and we get the power in electrical component. Translational, the effort variable, as you might expect, is the force, okay, something external that's incident, and I guess I should say it could be internal, but it's applied to the dynamical mass or system that we're investigating. And the flow variable, something that is maybe moving or rotating in some way, and that's actually the velocity, okay, to keep the units consistent. So again, angular velocity for rotational and regular velocity for translational. And the reason why this works out is that if we take a look at some sort of system, we know that the force times some sort of distance over which that force is applied is going to equal the work done on that system, which is also equal to the energy. We also know that the power, okay, over that process is going to be the total change in energy over the same amount of time. We all know that power is going to be energy divided by that time. Therefore, if we make some equation that force times the distance over which that force is applied is equal to the power times, I'll just have a regular t for time, and we manipulate this particular equation so that we have the distance over time is equal to power. We can see that indeed the force times a velocity, and maybe I'll add a little line right here and up here in my chart, okay, to distinguish it from voltage. So I'll make this kind of a capital V for voltage and a little lowercase v for velocity. The force times that velocity is indeed the power. And again, we have something right here called the effort variable, and something right here called the flow variable. And for all of these systems, we have two power variables that when multiplied together are going to be the power in the system. Well, we can look at things in terms of power, but we can also look at things in terms of energy. And if we look at the same sort of domains with respect to momentum and displacement variables, we can see that we can convert, say, V into, say, x dot or some other things, and fill out this half of this system similarity. We will first fill out the bottom row here in just a second. So in terms of, say, well, the potential energy of some sort of system, that's potential energy, not power times energy itself. What we need to do is we need to sum up, using an integral, all the power over that time. That's more or less just using this equation right here. Well, we know then that power, or P, so if I just did this, P dt, okay, we would sum up all the force times velocity times dt. That force is going to be perhaps maybe in a spring. So if it is in a spring like this, okay, we know that the force is going to equal to kx. So we're going to replace that force with something like this, kx, okay, times velocity times dt. This component right here equals dx. Well, why is that? Well, if v is equal to dx dt, then an infinitesimal x is equal to v dt. So we can replace that with the integral of kx dx. And then when we pull up k in the front and we do the integral, we get 1/2 kx squared, which is indeed the potential energy inside a spring. So this right here is one of the displacement variables. So we're going to go up here and replace displacement with x, because we can store some energy by compressing a spring and store some energy inside. Now what about kinetic energy? Well, we'll do the same sort of thing where we have sum of all the power over that given time. In this case, we're going to flip, we got the speed times the force times dt. Change in momentum with respect to time equals the force. So that means then that dp is equal to force dt. So we can now rewrite this equation as v dp. Now p itself is momentum, that's mass times the velocity. So if we plug that in, an infinitesimally small momentum value will be v m dv, assuming that assuming that the mass does not change. And eventually this is going to end up with a kinetic energy of 1/2 mv squared. And we use this equation right here, the momentum, or P for linear, the linear momentum is then one of the energy variables as well, usually used for the kinetic energy. Therefore, if we have P being, in this case, the linear momentum, and we can use either one of these for the two different types of energy for a mass in a translational sense. We can now come in here and replace, in a rotational sense, the angular momentum, and usually we use h for that. A displacement is going to be theta, such that if we have a torsional spring, the energy in that torsional spring would be 1/2, this is potential energy, k theta squared. And we don't go into too much, but there is energy variables of momentum in an electrical sense. In particular, we call that lambda, okay, and it's called flux linkage. The unit of displacement is q, or the charge. So you can see that there's a relationship between x and V right here. If we want to know what the flow variable is, we take the time derivative of the displacement variable, such that if we want current, it's the time derivative of Q right here. And in the same sort of thing, if we have a capacitor, we can make the same arguments, but the potential energy inside a capacitor is going to be 1/2 the capacitance of that capacitor times Q squared. All right, so now what about this bottom row right here? Well, there are effort and flow variables and momentum and displacement variables for fluid systems. There's also a fifth category, thermal systems, but there's an entire course dedicated to the thermal systems, and so we don't discuss those too much in this particular course. But in terms of fluid, there's an effort variable of pressure. Okay, this is now pressure. So there's a pressure difference. You're going to drive or propel some water or some other fluid down a pipe in some way. And there's usually capital Q used for the flow rate. This is very similar to current, charge per second. You might have liters per second or liters or gallons per minute. Okay, there's something flowing there. For momentum, there's something called pressure momentum. So I'll label that right here as pressure momentum. Kind of one way to store energy inside a fluid. That's a little P right here. And then the displacement is V, okay, for volume. Okay, in addition, these systems are similar in other ways. So I'll rewrite these real quick. And one of the ways is that they have relationships that satisfy different types of energy dissipation, such as resistors, storage, such as capacitance, and inertia. We'll start with the electrical since that's probably the easiest, but we can recognize that there's a component relationship we've been using it multiple times. And that is V, an effort variable, equals R, the resistance, times I, the flow variable. We also know about the force of friction. I'll put this little FF right here because that can resist, but there's other types of resistance. So for example, we might have FB as well, the force to a damper, and that's going to equal B, or some sort of coefficient, times the flow variable, V, right here. And rotationally again, we have some torque. I'll add F here to remind us it's friction or from a rotational damper. And that's also going to equal the coefficient, B, times the flow variable, omega. And so not surprising, there's going to be some resistance terms where we have pressure is going to equal the resistance in a tube or in a pipe. That's going to multiply by the flow rate for a component relationship inside a fluid system. Well, let's do for capacitance something in the translational side of things, and that is a spring. So we'll do Fs for spring. Okay, the force in a spring is going to equal K, some sort of constant for that spring, times a displacement variable, X, for the last column up above. So an effort variable for capacitance is going to be multiplied, or rather is going to equal some sort of constant times a displacement energy variable. That means then that's similar. We're going to have a torque, okay, maybe in some sort of torsional spring that we're going to store some energy, and it'll be K times, well, the displacement, theta. All right, in terms of capacitance for the electrical, okay, let's take a look at what it looks like. Well, we have the effort variable, voltage right here, and it's going to equal some sort of constant, okay, C, some sort of capacitance, times Q. It's hard to see because we haven't used that equation before, but if I take time derivatives of both sides, I can get voltage dot over Q dot. And now, okay, I can see that this is indeed C times I. This is not I dot, this is just I. And then the equation that we've been using is I equals 1 over C times dV over dt. And then we recast this value right here into just C. And that's why we've been using that component relationship, since it's a little bit easier to extract out the state variables, but it all starts from that original sort of capacitive equation, V equals C times Q. And it's even easier if we actually take the constant and divide it, or rather invert it right here. So 1 over c, 1 over c, and then this one becomes a c. Hopefully it wasn't too messy. All right, and then the last one, we're going to take an effort. So we got change in pressure right here. This is for fluid, and it's going to equal, well, sure enough, some sort of capacitance column, such as 1 over c times, well, a change in volume right here. And we'll discuss why this is the capacitive equation to use when we are defining a fluidic system. Okay, and now inertia. Well, let's start off with translational. Okay, and we knew that the momentum is equal to mv, mass times velocity. So there's going to be relationships where v, okay, the velocity is going to equal 1 over m times p. Essentially, we have a flow variable, okay, right here, and that's going to equal to some sort of constant, which is right here, times a momentum variable right here. So in a rotational sense, then, we will have the angular velocity equals 1 over j, some sort of constant term that's not going to change or vary with respect to time, times h, which is the, well, rotational momentum. So we have flow variables. We'll do this next one, which is I, that equals 1 over L times the momentum variable, flux linkage. So we know that if we have an equation with L, if we keep on solving for this equation, we can take the time derivative of both sides. So now this is I dot, and this is flux linkage dot. And ultimately, that's going to end up with an equation of V equals L di dt. This is an I right here. And this, of course, is the equation that we've been using to define the voltage across an inductor. Well, continuing with this pattern then, we will take the flow variable, that's Q, the flow rate, for power variables column, 1 over capital I, and then the pressure momentum times V, the volume. So what you'll find is that relations start to break down and they're less consistent for inertia. So here's a little summary down here. For resistive elements, we get effort is going to equal some sort of resistance times flow. For capacitive, we have effort equals 1 over the capacitance times the displacement. Or we could look at it this way. The capacitance is equal to a time rate of change of the effort. Oops, sorry, not equals, it's times equals the flow. So there's two equations right there. And then for inertia, down here, we had the flow variable equals 1 over the inertia times momentum, or we had the inertia term times ddt of the flow variable equals the effort variable. And the super summary, which I'll do up here to finish off this video, is that flow is equal to the time rate of change of displacement. And an example of that was that V is equal to dtx. We have effort, which is the time rate of change of momentum. And one to memorize is that the force is equal to the change in, well, translational momentum, linear momentum. And since flow times effort equals power, and power equals time rate of change of energy, we can get flow times effort equals the time rate of change of displacement times the time rate of change of momentum. This one down here, and this one right here.